Hello, everyone. Good evening. My name is Amin. I'm a theoretical physicist and a faculty member at the physics department at Ashoka University. So welcome to the second lecture of our online lecture series, Scientifically Speaking, an hour of knowledge sharing and interaction with a world-renowned scientist. Our aim with this lecture series is to introduce you to the cutting-edge research and innovative teaching techniques at Ashoka University. It is designed to break down complex concepts for high school students with the passion to explore the sciences. With a new topic and expert each time, we'll take you on a journey to explore a particular contemporary scientific subject. At the end, the speaker will answer your pressing questions. Before I introduce our first speaker, just a few logistics for this lecture. Our moderator, Rashmi, will interview the speaker, after which you can ask questions using the Q&A feature in Zoom. You can choose to share your name or send in your question anonymously. All these seminars are recorded and will be uploaded on the Ashoka University YouTube page for those who may have wished it or wish to revisit it at a later date. We will share the link for the entire series with you soon. Lastly, there will be a quiz to test your knowledge after this lecture. The top 5 winners will get a special gift. So tonight, I am delighted to introduce our speaker, Professor Xray Chaudhary, a highly respected astrophysicist and currently the director of the Inter-University Center for Astronomy and Astrophysics, also known as IUCA, in Pune. He graduated from Presidency College, University of Calcutta, and the University of Oxford in UK. After his PhD from the University of Cambridge, he worked at the Harvard-Smithsonian Center for Astrophysics in the US, where he was part of the team that built the Chandra Xray Observatory for NASA. After teaching for over a decade at the University of Birmingham, he was Dean of Sciences at Presidency University, Kolkata, before his current position. His work involves a wide range of topics in observational cosmology, astrophysics, and data sciences. His research interests lie in the study of the evolution of galaxies and on the supercluster filaments of the cosmic web. He has used optical, X-ray, radio, infrared, and ultraviolet observations to understand how the transformations of galaxies are related to their local and global environment. He is involved in developing machine learning algorithms for astronomical data mining. So Professor Ray Chaudhary visited us about a year ago and gave a fascinating lecture to a packed audience. It is great to have him again for the session.
Hi, Amin. Good to see you again. That was a very flattering introduction.
Thank you. Very good to see you too. Thank you very much for being here. It's great to have you here.
Thank you.
So we'll start our session without further ado. Let me introduce the moderator of this session, Rashmi, who is a talented undergraduate at Ashoka University, a third-year physics major and an astronomy enthusiast. So she will be moderating this session, and I'll hand this over to her.
Yeah, thanks a lot, Amin, sir. Hi, Professor Shomak, how are you doing?
Hi, Rashmi, how are you?
I'm good. I'm actually really excited to begin because I've been interested in astronomy for as long as I can remember, as you can probably make out from the telescope right next to me.
That's right. I was just looking at that. What kind of telescope is that?
Yeah, so it's actually an optical telescope. It's a 4.5-inch Newtonian reflector. On really good days, I can just about make out the rings of Saturn. But yeah, I'm hoping through this discussion that we can sort of see just how much astronomy can do. So I think without dilly-dallying further, let's just get right to it. So let's start with the idea that our idea of astronomy is, for many of us, built by looking at popular culture. So this idea of the astronomer building larger and larger telescopes to probe deeper and deeper into the sky. So could you walk us through maybe how astronomy has evolved and where we are today as astronomers?
Right. So I said that I'm going to talk about astronomy in general. When you look at how astronomy evolved, it's one of these sciences that has been around for hundreds of years, thousands of years, in fact, because even before the current era of astronomy, people could always see the stars. I mean, before our home entertainment television came along, the greatest entertainment after sundown would have been the skies, and you watch the skies, you see the stars turn, the planets come and go, comets come and go, and of course you needed to know the sky very well in order to navigate yourself, to go to the nearest village, or go long distances. You also knew what season it was, when the crops would be planted, when to harvest. All of this came from your knowledge of the sky. And so people would make up stories about the sky. They would connect the dots and imagine creatures in the sky and all that. And this is all naked eye astronomy. Naked eye astronomy was the what we did. And of course, we feared things in the sky. We also rejoiced when things happened in the sky. This was part of our life. But we started really studying the universe beyond this veil of stars when the telescope was started to be used. And that was from the early 17th century when people started building telescopes. And you see that still we are seeing with the eye. We're looking through a telescope. The middle one is Herschel's telescope, built in the 18th century, which became so big that we started looking beyond our own nebula to look at stars and nebulae all across the universe. And then towards the end, you see Hubble observing through the telescopes built in the beginning of the 20th century. And so by building these bigger and bigger telescopes, by the beginning of the 20th century, we started to actually get an idea of where we are in the universe. In the 17th, 18th centuries, we realized that we live on Earth that goes around the sun, and now we know that we live in a galaxy and things like that. And so you can see that with the small telescope that you have, you can look at Saturn, you can look at the planets, you can look at the moon as it's there. But most professionals would use a telescope that's, say, 2 to 4, 6 meters in diameter. The middle one is the telescope that Ayuka has for Indian universities, somewhere between Pune and Mumbai up on the Western Ghats. And that's the kind of telescope you would use. At the top end, the really big, looking at the other end of the universe, you use the Keck telescope, for example, which is there, telescopes that are 8 to 10 meter class telescopes. And those are in exotic places, in high and dry places, in deserts and tops mountains. And those are the largest telescopes that we have.
Right. So, I mean, just on this one slide, we've gone from like a few, maybe not even half a meter, smaller than that, to 10 meters. So really, I mean, why is it that we're interested in building larger telescopes?
Well, one of the things is, of course, larger telescopes mean that you collect more photons. And just you look through the eye, it's only the photons then come through the aperture in your eye. And what a telescope does is that it collects the photons from a much larger area and then put it in, but your eye is still the detector. But if you move away from the eye as a detector, then you can have a camera, and of course, then you can increase the integration time of the image, and then bigger and bigger telescopes along with the camera then give you a much deeper view of the sky. You can look at further and further objects. But there is another thing, and that is it increases the resolution of your image as well, because you want to see a very fine resolution, and we'll see what that gives us later on. But we know from fundamental physics, the physics that you learn at the beginning of the university, that if you are looking through a system that has a finite size, a telescope's mirror, say, then the size of the mirror introduces a limit to the resolution, and that's called the diffraction limit. And that is given by this ratio, the wavelength of the observation divided by the size of the telescope. And this is why, as you go to bigger and bigger telescopes, that delta theta, which gives you the fine resolution, becomes smaller and smaller, and you can see more detail in your image. Now, your eye can see roughly up to about a second of arc, which, as you know, 3,600 seconds of arc in a degree. But then as you start increasing that d, even for the same kinds of lambda, which is the wavelength, you start seeing finer and finer things. Okay. Of course, if you move away to a different lambda, say, look at the radio telescope, the lambda is very large, the wavelength, and that is why even with the biggest telescopes, radio telescopes we have, single radio telescopes, the resolution isn't very good.
Right. So how do we really overcome this resolution problem with radio telescopes on the ground?
So that's where, and we'll look at this later. What we do is we take a bunch of radio telescopes, different radio telescopes, and use them all together. Here is a picture of the GMRT, the Giant Meter Wave Radio Telescope in India, north of Pune. And here we have 30 different dishes spread around in a Y among vineyards between Pune and Nashik. And what we're doing here is that we are combining the signals that come from each telescope and combining them together so that in the lambda over d formula, the d becomes the distance between the farthest dishes. And so in effect, you have a telescope that's 30 kilometers big. You can't do this with the optical wavelengths because our wavelength is very small. And so we have problems with coherence. But in radio, we can do this. And this is how we get the highest resolution images that we have. They come from radio telescopes. Even those single dishes amongst radio telescopes don't have that kind of resolution.
Right. So it seems to be that the astronomers really sort of putting all this together, right, from visual and radio.
So that's right. So what happens is that what the radio telescopes tell us are very different from what the visual telescopes tell us.
Right.
And so once we started going into radio astronomy towards the beginning of the 20th century, we learned that these are two different things. And so we started getting data about the same objects from different kinds of light, of radiation. And thus we started piecing together clues as a detective would. And so what happens in astronomy is that the astronomer can't really go and touch and go and visit our subjects, unlike many other kinds of laboratory-based scientists who can actually construct an experiment and repeat the experiment and things like that. So we have to depend on the light, the radiation that comes to us. And so the clues that come from the radiation that we detect, we can make our detectors better, our telescopes better, but also go outside our different methods of detecting the radiation and gather as many clues as possible. Some of these clues are flawed clues, some of them have big noise in them. And so the astronomer is then the detective piecing together the faded clues, as it were, to understand, to build up a story of the universe. And this is why we have the talk named after this poem from the Victorian era, based on an Indian legend of the blind men, women, and the elephant, where each person in this image is trying to find out what the elephant is like by touching a different part of the elephant. So to one, the elephant is like a rope, the other is like a pillar, the other is like a fan, but only when you put all those individual views together, like the radio image and the optical image and the images in the other parts of the spectrum, can you then understand what a particular object is. And then this is why astronomy is a very young science, because we only started doing this in the last century.
Right. So could you tell us a little more about the electromagnetic spectrum? Because you've been mentioning this a lot about getting information from various parts of the spectrum.
Right. So when we see light, the light that we see is only one kind of part of the spectrum, one kind of radiation. There is also different kinds of radiation. They all come from the electromagnetic fields that exist in all objects in the universe. If you look at this, you'll see that increasing energy goes with increasing frequency. As the wavelength increases, the energy of the radiation decreases. So we go from light to microwaves to radio. As the energy decreases, higher and higher energy radiation would be ultraviolet, X-rays, and gamma rays. In all these different parts of the spectrum, you get different information from when you're the detective piecing together the story. And as you can see, our eyes are sensitive to a very tiny part of this whole spectrum, only from wavelengths of 400 to 800 nanometers, right in the middle.
Right. So when we look at stars, even in the night sky, if it's a clear sky for you, then it's sort of apparent to make out that some stars shine a little more redder, some a little more bluish. So, I mean, there are also different parts of the electromagnetic spectrum. Are they trying to send us different information? And so before we take you up on that, let's just see what our audience has to say. So one sort of thing that we could think of is, do you think hotter stars shine bluer or redder? So this is a poll for our audience. The poll is going to be up for about 30 seconds. And yeah, let's see what our listeners have to say about this. I've sort of studied, so I know what the answer should be, but I'm always confused when I think about it for a second. Right, I think we can close the poll in about 5 seconds more and we can see the results.
It's
All right.
Yeah, it's wonderful. It's very interesting to see that the opinion is so divided amongst people. And, I mean, when we talk about things getting hotter, we say red hot. And that's why we think that hotter things are red. But actually, bluer stars are hotter. And as something gets hotter and hotter, the energy starts increasing, the frequency starts increasing, the wavelength starts decreasing. And so we move from the red end to the blue end. This is the Planck spectrum, the spectrum of a star or anything that is radiating as a perfect body, a black body. And so that's what this is first year physics. What happens is that something that's radiating at a certain temperature, as the temperature increases, the peak of that moves towards the blue end of the spectrum. And so here, for example, are 3 stars. And the middle one is like the sun. Surface temperature is about 6,000 Kelvin, and that's why it's yellow. A star that's much hotter, a younger star, would be 20,000 degrees hot and would be very blue. A lot of its radiation will come out in the ultraviolet, and redder stars, which are cooler, would be on the right hand side. And the entire energy that comes out of a particular star is the area under that curve. And
sorry, just to interject here, it seems like the height of the curve doesn't really matter. It's more the position of where the peak occurs. So
no, the position of where the peak occurs gives you the color of the star.
Right, that's what.
But you can see as the star gets hotter, the area under the curve also increases, and that means that it gets brighter and brighter. That gives the total energy that's coming out. So blue stars, young stars, are much brighter and bluer than the red stars, which are fainter for the same kinds of masses. And so this is contrary to what many of the people thought, which is that, and actually this is what happens when you heat up a metal as well. It gets bluer and bluer as it gets very hot. And so the hotter stars, but our star is, as you know, the sun, which is a very middle of the range, boring star, as it were. It's our star, so it's special. And that's right in the middle, and most of its light comes out in the middle of that visible range, the range that's marked up there, which is what our eyes are sensitive to. We can't see anything, on the right side or the left side of that mark, the visible light range.
So it's possible to look at the sun through different filters because it is in fact emitting throughout the range, even though we can see only a part of it.
That's right. So when we look at the sun, we see this yellow disk, maybe with a couple of sunspots, but we don't look at any features. But the real fun starts when we start looking outside the visible range. And we have telescopes and instruments that can see the ultraviolet and the infrared and the X-rays. Then we start seeing what the sun really is. As you can see, it's the same scale, but you see that sunspot in the ultraviolet from the Solar Dynamics Observatory turned into these amazing huge areas, which are sunstorms going on. We can look at high energy particles coming along, magnetic fields surrounding those sunspots, and the sun looks far more interesting and tells us a lot more about what's happening on the surface of the sun. Now, these these particles that are generated in these sunstorms would actually come and hit the atmosphere of the Earth and cause the aurora borealis, and we wouldn't have known the reason for that if we hadn't seen the sun in the ultraviolet and the X-ray.
Right. Yeah, that's very interesting. But I mean, well, so far we've been looking at the sun, which is obviously out there. It's an astronomical object at the end of the day. But if the sun can emit in different wavelengths and we can look at it through different filters, can we look at something closer home? Perhaps, you and I, are we emitting anything other than what we can see?
The sun is 6,000 degrees hot, and so it's light. You and I, our body temperatures are 300 Kelvin, and so we emit in the infrared, in the near infrared. And so if we actually are seen in a dark room, you will see that we emit a few watts of radiation. We're like a 1 watt bulb, but emitting in the infrared. Our eyes are not sensitive to infrared, but we don't see, that's why we don't see them. But say cats can see the infrared, and so they would see you in the dark. As you can see, this is an infrared picture of this man holding up his hand in the inside a plastic bag. The plastic bag is a different temperature. You don't see that, the plastic bag. You can see through the bag, but you can see the hand. You can see that even in an infrared camera picture, this is taken with a night vision camera, say, which is in our phone, and you can see the things glowing in the dark. You see the hot plate has different views as it's turned on. The butterflies have different markings in the infrared than in the optical, where we see reflected sunlight. And even on our body, different parts have different temperatures. And that is what you see in that image. Our eyes are cooler than our face, and our hands have a different temperature. And so certainly we are emitting, and this is why we know that everything in the universe is emitting some kind of light.
Right. And
it depends on their temperature.
Right. So can we talk about an astronomical object now, about something other than our sun, because that's just too close to home. So what about looking at, say, like we're looking at the Orion Nebula now at different wavelengths?
This is one of my most favorite pictures. You can see the constellation of Orion, which everybody knows, the Orion the Hunter. You have Betelgeuse right on the top corner, but we often see the Orion Nebula, a small telescope, and this is taken by a telescope at your university, a lovely picture in the optical, taken by a small telescope of the nebula, which is right in the middle of the sword of Orion. Now, this is what an optical telescope tells us. It shows us there are lots of stars in that little nebula. You also see a little bit of nebulosity, and that's why it's called nebula. It's light reflected around from the gas and dust that's around the stars, but that's all this optical picture tells us. But if you then move away from what our eye sees through a telescope to other parts of the spectrum, then you can see all these amazing things that are happening in the same nebula. So you can see optical and ultraviolet from the Hubble Space Telescope on the top. But as you move towards the infrared, the same place glows and tells us that what's happening in that nebula is that that's a stellar nursery. Lots of stars are being born there. And the Orion Nebula is actually part of the Orion Arm. There are 5 arms in our galaxy, the Milky Way, and that's where stars are right now being born. And you can see in the ultraviolet those stars, some of these newborn stars, which are 20,000 degrees hot, but their ultraviolet light shines through the dust that surrounds these. Now, where stars are being born, there's a lot of dust because this stellar birth is messy. The stuff that's going into the stars, a lot of it is left around. It's like in my kitchen when I make chapatis, flowers all over the place. So dust is all over the place. And what's happening here is that dust is absorbing some of this light that's coming out of the newborn stars, and it's glowing at temperatures of a few hundred degrees, like our bodies. And that is why it's in that's why they emit infrared. So this is the Spitzer Space Telescope, the Herschel Space Telescope images show them the true nature of the Orion Nebula, where we see the dust glowing at temperatures absorbing light from the newborn stars.
Yeah, I mean, these are absolutely gorgeous images, all 3 of them. They're just so beautiful.
There are images from all over the spectrum of the Orion Nebula now. It's so close by, and they're absolutely beautiful.
Yeah, yeah. Well, anyways, you've mentioned that actually each of these images are taken from telescopes in space. So, I mean, why go to space at all?
Well, we have to, because what happens is that along the electromagnetic spectrum, it's all very well to say that different temperatures give different kinds of light, but they don't reach us on the Earth. As you can see here, along the atmosphere, along the electromagnetic spectrum, the atmosphere only lets in optical light, the light that we see, and some radio waves. But the rest of it, infrared, ultraviolet, X-rays, gamma rays, they're all stopped by the atmosphere. And so the water vapor in the atmosphere absorbs the infrared. So that's why to get those pictures of the Orion Nebula, you have to go to space above the atmosphere. It's also very interesting. It's a coincidence, isn't it? That our eyes see a very small range in the electromagnetic spectrum, 400 to 800 nanometers, but it's only fine-tuned to that window we have in the atmosphere. Just imagine if, for example, our eyes were sensitive to, say, just twice the amount in wavelength in the infrared, we wouldn't have known of stars outside our atmosphere. We wouldn't have known the existence of the universe. I mean, you can think of certain rattlesnakes that can only see in the infrared, you now know why there are no rattlesnake astronomers, because they don't know the existence of stars.
Yeah.
And then what happened then in the beginning of the 20th century, we realized that radio waves are also coming through the atmosphere.
Right.
And then we started from the 1920s building radio telescopes. But
Right.
the real kind of multi-wavelength astronomy, the detective kind of astronomy I'm talking about, had to really wait till the second half of the last century before we started sending telescopes into space.
Right. So let's talk about space-based astronomy for a bit, because we've spoken about radio and visual, but what about detecting, say, waves and information at the higher end of the EM spectrum?
So here, I mean, this is both higher and lower. You can see that
Right.
Herschel and Spitzer are telescopes that catch infrared radiation,
Right.
and Chandra X-ray telescope is at the higher end of the higher energy part of the spectrum.
Right.
You can see that they look very different from that telescope you have behind you, right?
Yes.
Because here, in the infrared, the telescope itself emits a lot of radiation.
Right.
So you can't have a mirror just making images without cooling it and making sure that the temperature, the telescope itself is much cooler. And that is why you have that great sun shield in the Herschel telescope that is blocking sunlight coming and heating up.
Right.
And so that's one way. And then the detectors themselves have to be very different from the kind of normal cameras we have in our telescopes. Similarly, the Chandra X-ray telescope at the higher end of the spectrum detects these X-rays in a very, very different way. The particle physicists have ways of detecting high energy photons, gamma rays, and X-rays and particles. We borrowed their technology for their detectors, and the telescopes work in a very different way. Here's India getting into this game. About 5 years ago, India launched the first space telescope called AstroSat, which is working wonderfully. There are 5 telescopes. And the unique thing about AstroSat is that it can observe from the optical through UV to X-rays using these 5 telescopes simultaneously. And it can tell you what's happening, how things are changing across the spectrum. And so this is the first space telescope that India has launched. Right. We are soon about to launch an ultraviolet telescope for the sun called Aditya. And there are plans of doing some wonderful other space telescopes from India to study these objects from outside our optical spectrum.
So you've spoken about the Chandra telescope and how the mechanism that it uses to create images is very different from, say, my telescope next to me. So, I mean, how does it work?
Yeah, that's because, of course, as you know, X-rays go through matter, right? So the X-rays, the wavelength of X-rays is very similar to the interatomic spacings. It goes right through. And so in order to do an image, if you actually reflect the light that comes from something, X-rays won't be reflected from a mirror, it will go right through. So on X-ray telescopes, what you have to do is you have these X-rays coming and they have to graze by the metallic surface that is the mirror, and slowly they have to be, and this is called grazing incidents, deviated at very small angles and then shepherded towards the detector. So X-ray telescopes are very long and the mirrors can actually be nested. Here there are 4 mirrors and all of them are slowly focusing these X-rays towards that instrument right at the middle. And that's an instrument that's very different from the cameras that we use. So the entire technology of building the telescope and the detector in the Chandra X-ray telescope and similar telescopes is very different.
Right. So, I mean, let's look at an example here about using very different kinds of telescopes to do imaging of a certain galaxy. Could you speak about Centaurus A?
Yes, so that's why we go to the high energy part of the spectrum. Now, for example, if you start from the 2 images that are in the middle, you see the visual image is very similar to the Orion Nebula that you saw. Visual image is what you see through a normal telescope, slightly bigger than the one you have behind you. And that tells us that this galaxy has resulted from 2 spiral galaxies colliding with each other, and it's created that dust lane in the middle, which is like a mustache going through. That dust lane is dust, so it glows. And in the infrared, just as you saw in the Orion Nebula, you see that glowing in the image that you see there from the Spitzer telescope. And it's lovely, the dust glows. So those 2, you can see the correspondence. But But then you then ask the question, what's happening in that galaxy as a result of that collision? What has happened? It turns out that it has a very big black hole right in the middle, which is 1 billion solar masses, and it's heating up the gas that's in the galaxy to many tens of millions of degrees. And this is the left-hand side image that you see, which is something that I worked on with my team using the Chandra telescope. That's a result of 1 million seconds on the Chandra telescope, giving a lovely view of the X-ray emitting hot gas. Everything that you see in that image is more than 10 to the power 7, 10 million degrees hot, whereas anything that you see in the visual plot is a few thousand degrees hot. So you can see, you get a totally different view. You can see what's happening to the black hole. You can see the hot gas surrounding it. And then you ask the question, why is the gas so hot? Why is it millions of degrees in between the stars? And that answer comes from the radio image right at the right, which is a radio image that comes from something like the GMRT, and that maps the very fast-moving electrons that are coming out from the surroundings of the black hole in the middle. Those electrons are moving at 99% of the speed of light, and their energy is transferred to the gas that's in between the stars, and is heating them up to these X-ray temperatures. So you can see how the detective in this case has got those clues together from different telescopes, different technologies, and brought them together. And we can also already see the volume of data that you need to bring these together, because each of these telescopes produces gigabytes and terabytes of data. In producing any of these images, in order to bring them all together, we need to work on very large data sets and understand what's going to happen. In order to look for different features of them, we need to use various things that big data scientists use.
So I think I particularly like this example because it shows you that if there was even a part of the spectrum that we weren't looking at, I mean, just a whole aspect of this galaxy would just be, hidden to us. So that's lovely.
The elephant and the blind people, right?
Yes, back to that again. Yeah. And but anyways, while we're on the topic of Centaurus A, you mentioned the black hole in the middle. And when you think about a black hole, a lot of talk recently has been about the black hole imaging, right, in M87. So could you tell us a little bit about that?
So M87 is a galaxy which is about 3 times as far away as Centaurus A is from us. Right. It's in the central galaxy of the Virgo cluster. It is a round galaxy, an elliptical galaxy. It looks very boring in the optical, but when you have an optical image, that's there in the middle of the Virgo cluster. And we've known about it for a long time. It was in Messier's list that was made 200 years ago, taken by a small telescope. Now, once you start looking at in great detail with the Hubble Space Telescope and zoom in the middle, you see lovely things that are coming out. In there, you see a optical jet. Now, the blue is the X-ray gas that's from the Chandra X-ray telescope, which fills the galaxy. You then ask what's happening, why is there hot gas? And then you start looking at the jet just coming out of the middle of M87, and here you're zooming in right towards the middle. You look at the radio jets that are picked up by the VLBI, a large array of radio telescopes that tells you that something's happening. There's a big black hole in the middle, which is a few billion times the mass of the sun, and then you start connecting the black hole to the gas. But the interesting thing that happened now is that this, for the first time, we have been able to image the black hole. There was a lot of discussion in the last century. Stephen Hawking had this bet with other people that we'll never be able to image a black hole because we won't be able to really go right to the middle. Here, you look at this image, which is a beautiful image. To me, it looks like a medu vada in the sky, which is very edible. But if you look at the actual, the size of that image, it's 10 to the power 5 times, 1 lakh times more fine than the resolution of your eye. This is the highest resolution image that we've ever seen in astronomy. And in order to go there, in order to actually find the edge of the black hole, of course, you can't see inside the black hole. You really needed a very high resolution image. Otherwise, you couldn't really go and see what's going on directly from the black hole.
Yeah, the reason I like that video is because it shows you that when you zoom in, you just have to zoom in so much and you go on and on and on until you finally get to the black hole, you know? And so anyways, at this point, I mean, I think our audience has also got a sense of really how big this project has been to image the black hole. So let's have a poll. How much data do you think was needed to create the black hole image from the Event Horizon Telescope? So we've got 5 options, and let's see what our audience thinks of that. I think about 10 more seconds, and then we can display the results.
Remember, most modern laptops have 500 gigabytes of data.
Okay. Wow, that is surprising. I wouldn't have guessed that.
That's actually pretty advanced. I mean, it just shows that a lot of the people who are listening to this talk are have been paying attention.
Yes.
It's very interesting, isn't it? Because you see a very blurred kind of a donut-shaped image, which looks like it doesn't have much of information in it, but it did require petabytes of data, 5 petabytes. Right. And that all that data, it comes together to create that image because of the resolution. It was images that came from all these telescopes all over the world, from Antarctica to the Canary Islands, to Hawaii, to the US. And these are telescopes that operate in the millimeter wave, in the radio. And together, the thing is, for 5 petabytes of data, you could not transfer over the internet. So they had to be backed up on tapes and physically brought together and combined. And I was talking earlier about the GMRT and the radio telescopes, how you can combine data from various radio telescopes to produce these high resolution image. And here's the highest resolution image we've ever had. And it shows the power of big data. There is no way, even a decade ago, we could have processed that kind of data with the computers we had then. So we are now, entering this era of doing telescopes the size of the Earth, because the resolution of this telescope is so big.
Yeah, I mean, that's so cool, because I mean, in half an hour, we've gone from the little telescope next to me to a telescope that is the size of the Earth. So that's just a huge journey that we've come through.
Well, if we put one of these telescopes on the moon, then we can have a even larger telescope.
Right, that's right, yeah. But okay, so we're still on the topic of black holes. And something else that's been talked about a lot on this topic is, of course, gravitational waves. So where does that come into the whole picture? Because as of now, we've been just speaking about the EM spectrum.
So we're talking of the electromagnetic spectrum, but you see, I mean, electromagnetic spectrum, the radiation come from variations of electric and magnetic fields, which are in various stars and galaxies and in between. But not all objects have electrical and magnetic fields. It could be that they don't. And for example, black holes don't. But then everything in the universe has mass. So and Einstein, when he formulated the theory of gravitation 100 years ago, said that this as a result of everything having mass, if they move around, they can create gravitational waves as the ripples in the fabric of space-time. And so, but then he also said that there is no way we would be able to detect it, because the ripples would have amplitudes that are smaller than the size of a nucleus of an atom. This is something that, of course, we detected 5 years ago, and the Nobel Prize was given a couple of years ago. And so this is about the strongest source that you can have, 2 black holes merging. And what's happening here is, as the 2 black holes merge, it's a matter of seconds, the ripples that they create in the fabric of space-time is detected. Now you can see that this is a kind of a clue, a detective clue, that is very different from the electromagnetic radiation. Right? It comes from a very different source. It is caused by different physics, and so it just increases our number of clues, immensely, because and then gravitational waves are also of different wavelengths and frequencies and energies. And so we now then call it multi-messenger astronomy, where the information comes from different parts of the spectrum of both gravitational waves and electromagnetic waves.
So, I mean, could it be said that analogous to the EM spectrum, there is a gravitational wave spectrum that, I mean, so that you detect waves across it, or short wavelength, long wavelength?
The ones we have now detected are in the hertz range, from about 1/10 of a hertz to about 100 hertz. But then you need different kinds of telescopes, gravitational wave telescopes.
Right.
Then just like the X-ray telescopes or the infrared telescopes, and then we'd be able to detect nanohertz or megahertz of gravitational waves, and that will give us information about various other kinds of sources, supernovae, Big Bang, things like that.
So for us as students interested in astronomy, there's been a talk in the last couple of years about India having an observatory. So is that true? I mean, are there opportunities for us?
There you are. And these gravitational waves were detected by the first 2 gravitational wave observatories in the US, the LIGO observatories. Then Virgo in Italy joined them, and we'll soon have another one in Japan. But in India, we're going to build LIGO India, which will be the 3rd LIGO observatory. And we're working on it together with the US, but it will be built entirely in India. This is a blueprint of what it will look like. This will be in the middle of Maharashtra, near a place called Hingoli. And hopefully later this year, we'll start building this. We've now acquired the land. And by 2026, we hope we will have an operating gravitational wave observatory in Indian soil. And there you are. And so people in India, students in India, scientists in India will be able to work with such a unique instrument on Indian soil.
Yeah. That's very exciting. I mean, for me, I'm a 3rd-year student, and it's exciting to know that there's something to do now, something to look forward to.
But you can see that, I mean, this will start working in 2026. The biggest telescope that we are building, the 30-meter telescope, will be operational from 2030. The youngest people who are going to use this are people like you, who are in undergraduates at universities now, or are in high school. And so this is a huge opportunity for you. And to some extent, I envy you, because when we were students, we didn't have such facilities, experimental facilities, to look out for within India. We knew that if we wanted to be experimental astronomers, we had to go abroad to do such things. And certainly your generation, people who are coming into university now, will know that in order to do world-class experimental physics, we will have these amazing facilities in India.
Right, but these facilities are still, I mean, maybe for those students who are more experimentally bent or, computationally bent, what about, I mean, other opportunities for those who are more interested in the theoretical sciences?
Yes, of course. And, I mean, India has always been in the forefront of theoretical sciences in physics and in maths and chemistry. And so we've had that tradition of theory, but theory can't work without experiment, and experiment can't work without theory. And so Amin, it must be still around. Amin is a theoretical physicist, and for example, for him to work on black holes and theoretical physics and the theory of it, to be confronted with experiments that we can make from within India is something very unique, and the students can see both communities working together.
Yes, so if I may interject at this point, I actually wanted to maybe get your take on something. So as a theoretical physicist interested in gravitational physics and black holes, what is your take about the theoretical implications of gravitational wave astronomy? So just to set the context for what I'm asking. So many of those in the audience would have heard about the direct detection of gravitational waves due to black hole mergers, which you were just discussing. And there's, of course, much excitement about how this potentially opens up new frontiers in astronomy. So as you mentioned, gravitational waves are a prediction of Einstein's theory of gravity, which is general relativity. But of course, it has been realized that they also afford an opportunity to constrain or rule out theories of gravity beyond GR, including modified gravity theories, higher dimensional models, and the like. And also, they may allow us to investigate properties of black holes, such as the structure of the event horizon and its dynamics. So what do you think is the scope here? If you could please throw some light on this for the benefit of our audience.
See, physics builds up on observations. And so Newton gave us a theory of gravity, and that was enough to, for example, explain why planets move around the sun. But you couldn't have, for example, given a description of black holes. Einstein, 100 years ago, gave us a new definition of gravity, which is slightly more general. And we know that that's not the last word. It's not the end of the story. We need to figure out what that is embedded in, what kind of more general theories there are of the universe, how can the theory of relativity be combined with quantum mechanics? Is there a quantum theory? And things like that. And we have to do experiments like this. The gravitational waves, you saw black holes. We are understanding black hole physics. Those are things that stretch the theory and also stretch observations. You're making cutting edge observations. Only yesterday we announced the discovery of gravitational waves from the LIGO-Virgo collaboration of the merger of two black holes, which were very different from each other, 30 and 8 solar mass. And that in that gravitational wave, we started looking at first detecting higher harmonics of the gravitational waves. Those give us definite predictions from theories of gravity like relativity. It rules out predictions from rival theories and also modified theories of gravity. And then slowly we will start understanding the modified theories of gravity that you work on and look at their predictions and look at signatures in these direct detections of black holes and neutron stars and other compact stars emerging. So here is a wonderful way of where our two worlds meet, and we can then together bring up the next generation of students working on such problems.
Thank you very much. So we'll move on to the Q&A session now, which again Rashmi will be moderating. So I'll hand this over to Rashmi.
Thanks, sir. Yeah, Shomak sir, thank you so much for this session. I think it's been very exciting for me, and I hope so too for the audience. We've had 350 participants and over 50 to almost 60 questions. So, I mean, there's a lot to dive into. So let's start with the Q&A session now. Okay. The first question is from someone anonymous. And they say that if these images that we're looking at in the ultraviolet range, I mean, if it's in the ultraviolet range, why is it colored?
Well, I mean, that's colored to, it's false color, of course, because we actually in professional astronomy, we never use color cameras, even in the visual, because they are not very good in terms of sensitivity. We take essentially grayscale images taken with various filters, and then we combine them. When we combine them, we use color to show various features, right? Right. So if I put an ultraviolet color on that image, you won't be able to see it with your eyes. So right. They are colored in what we can see. But the color is just to guide your eye and look at variations in, say, temperature or flux along an image. And that color does not represent the actual color. Right. Yeah, we try to make it as close as possible. So something that's blue, I won't put red color on it. But yes, so these are, the color is just to guide the eye and show variations in certain certain parameters like temperature or flux.
Right. So our next question is from again an anonymous person. They say, why do observatories like NCRA use array of telescopes?
Right. So this is something that I actually already mentioned, and that is in NCRA, for example, has GMRT, which is a radio telescope. A radio telescope on its own has very limited resolution. Even the largest radio telescope like the Arecibo, I showed in that calculation, has a pixel size that is much larger than most things that we observe, galaxies and stars. And so we can't resolve them, we can't get features. And so what radio telescopes do is that they have this particular property that you can combine information from various radio telescopes and build together images that are much higher resolution. Okay. If you combine them in a method called interferometry, then what happens is that you can get this high resolution, which is, if you look at the lambda over D formula, the D is the size of the array, not individual telescopes. And so if you have in GMRT, for example, the farthest dishes are 30 kilometers. And so you have a telescope the size of 30 kilometers. You can't build an optical telescope that big or a single telescope that big. That's why you use arrays. And the power of that was shown in the M87 black hole image, where we had telescopes all over the world.
Right. So our next question is from Yash, and he asks, what is Spitzer?
Spitzer is named after a very famous astronomer called Spitzer. Actually, Spitzer was one of the people who designed the Hubble Space Telescope. And but the Spitzer telescope in space is an infrared telescope. that measures temperatures, no, measures radiation. It actually images radiation coming from extraterrestrial objects in the range of a micron to about 30, 40 microns. And so going up to 100 microns. And our eyes go up to about a micron or so. So this is beyond our visual range. And so it looks at cooler stars, redder stars in the near infrared, and in the mid infrared in 50, 60, 100 microns, it starts looking at the dust that's there in objects at temperatures of a few hundred degrees.
Right. So all those pictures we saw of Orion initially,
that's right,
about the dust, right? That's where it comes from.
Yeah, absolutely.
Right. So our next question is from Satish. He asks, are most astronomical images we see created from data from multiple parts of the EM spectrum or only one?
Well, it depends, you know. I mean, you can take an image
Right.
from one telescope and it could be lovely. You saw images made from the single telescope at the University of the Orion Nebula. You saw telescopes, images of M87, Centaurus that we showed, which were taken by single. So actually, you can be an astronomer who's happy with just one image from a particular telescope. You learn a lot about it, but about your objects from just one image at one wavelength. But what I was trying to say here is in this mode of a detective, an astronomer can get a lot more information from using multiple different kinds of telescopes and combining this information. It gives us a lot more than the individual images. So 2 + 2 becomes much more than 4 because
Right.
you start putting together the information.
Our next question is from an anonymous person. They ask, what are the limits of the wavelengths that space-based telescopes can detect? And I think what limits this?
Well, different kinds of, very, very good question. Different kinds of, because I said that the atmosphere on Earth limits our different kinds of parts of the spectrum because it absorbs it. In space, theoretically, there is no limit because there's nothing there to absorb. But what happens is that there's, of course, the solar system, and then there's the galaxy. So, for example, within the solar system, in between the planets, there's dust that's left over by comets.
Right.
And that absorbs some part of the spectrum in the infrared and in the optical. You can see it glow on a very clear night called zodiacal light. And so there is a limit there of just the dust that's in between the planets, and we have to go outside the planetary system, our solar system, to get rid of that. We can't do that. Similarly, in between the stars in our galaxy, there is a lot of gas and dust and very high energy particles. If you are, for example, observing in neutrinos or gamma rays or things like that, that you could have limits because of the gas in between the stars. So those are the things that limit observations, the power of our observation at other wavelengths from space.
Right. Our next question is actually interesting and something that even I had wondered about. Why do we need so many gravitational wave observatories? I mean, isn't one enough?
Right. Of course. You see, gravitational wave observatories on their own are even worse resolution than radio telescopes. They are like a microphone. So if you have a microphone, you can detect a sound, but you don't know where the sound is coming from. If you want to find out where the sound is coming from, you need 2 and actually 3 microphones can help you triangulate. So gravitational wave observatories can tell you that there's gravitational waves coming, but they can't tell you where it's coming from. If you have 2, like the LIGO first detection, one of them detected it 7 milliseconds before the other. And so we knew that there was one part of the sky the signal was coming from, but we didn't know where exactly. We couldn't pinpoint it to a particular star or a galaxy. Now, having 3, and the third one being so far away from the US, and this is why India was chosen. Actually, initially, in the history, what happened was Australia wanted the US wanted the 3rd observatory to be in Australia because that's the farthest away from the US. But then the Australians couldn't come up with the money to build the 3rd observatory, and then India was offered, and India said yes, we were going to do it. we have enough people here interested to do this, and we got the resources to build this. Now, what happens is that you have these 3 observatories, 2 in the US and 1 in India. Then our capacity to pinpoint where the gravitational wave is coming from goes very fine, and we have a part of the sky that's maybe smaller than the full moon where we can pinpoint, and then we take our other telescopes, the optical and the X-ray telescopes and radio telescopes, and we look in there to find where it could have come from, and then we can find the electromagnetic waves that were generated from that event that caused the gravitational wave.
Right.
Luckily, we discovered one of these last year, not because what happened was this event of the coalescence of 2 neutron stars gave out gravitational waves, and it also gave out all these other kinds of electromagnetic waves. And we learned a lot about this event from all these observations. Now, that was serendipitous. When LIGO India comes up, and then the one that's coming up in Japan comes up, called Kagra, we will be able to pinpoint these as a matter of routine and try to find electromagnetic counterparts of these gravitational wave events.
So we're actually almost nearing the end of the hour. So let's wrap up with our last question. This is from Gauri, and she asks, how did the astronomers know that the image of the black hole in M87 would be in radio waves and not in, say, microwaves, for example?
Well, actually, it is microwaves. It's nearer to microwaves, but microwaves we often call it. It's similar to radio waves.
Right.
Low energy photons, millimeter waves. These are the thing is that what we are observing are the particles moving around at very high speeds in the magnetic field that is in the material around the black hole. And those things, as you saw in the images of the jets that you saw from GMRT in Sene and similar things, emit in the radio and in the millimeter waves and the microwaves, things like that. And so there's a particular signal that comes out of the processes that happen in these particles that move around the black hole. And the best place to find it is in the millimeter wave, microwave region. And so the telescopes that were used were telescopes that are sensitive to this particular part of the spectrum. Actually, it's very interesting that the first detection of these microwaves was done by Jagadish Bose in India more than 100 years ago. And the microwaves were discovered by him in Calcutta, in India. And then that technology that Jagadish Bose developed in the 1890s was actually used in imaging now.
Wow.
In these big microwave telescopes that we have. The same technology 100 years later, Jagadish Bose would never have known then that this is the kind of culmination of what he had done 100 years ago. But it turns out that the processes that produce that kind of radiation there around the black hole are in the radio, and this is why. And the other thing is, of course, in the radio, we can combine these telescopes all around the world to produce a high resolution image. That kind of resolution we would not have been able to get in the optical telescopes, because that doesn't give us micro arc second resolution.
Well, sir, our hour is up. I'd love to continue, but I think we'll have to end for today. So thank you so very much for being here with us. I mean, I found the session absolutely wonderful. I hope our audience agrees. And just thank you for spending so much time with us today.
Thank you, Rashmi. It's been a pleasure. And thank you very much for the audience for being here.
Thanks, sir.
Thank you. Bye.
Bye. Well, as a conclusion to Professor Shomak's session, we have a short quiz to test your knowledge. On the chat feature, we've sent a Google link form that you can click to open the quiz. Click on that and you'll have 4 minutes to complete it. On behalf of Ashoka University, I'd like to thank all our participants for joining us for the second lecture series of Scientifically Speaking. We hope you've enjoyed this session. We would appreciate your feedback for this seminar. Please fill the 30-second survey that will pop up on your screen after you leave the lecture, as this will allow us to improve on future seminars. Follow Ashoka University on Instagram and Facebook for updates on the next lecture. Thank you. Have a great week ahead and see you next Tuesday for the next Scientifically Speaking lecture. Thank you very much. Good night.